Everybody, this is a review lesson on molarity because you already learned in Unit 2 earlier this year how to calculate molarity and manipulate the equation a little bit to calculate some different variables about a solution. So this is a review, and I'll just go over it very quickly and give you a couple of examples, and then you can get a worksheet and practice what we've reviewed. By the end of this, you'll definitely be able to define molarity. If you don't remember what it is, you should be able to remember it by the end of the lesson. And you should be able to use your algebra to manipulate the equation and solve for any of the variables. And then here's what's new about this, though. We're going to talk about and we've been talking about ionic compounds that are soluble in water and how they split into ions. So what we'll do today is show you how to combine that information with what you already know about molarity to calculate the concentration of just a single ion in the solution instead of like the entire solute. Now, hopefully you remember this from, earlier in the year, that molarity, the definition of it is that it's the moles of solute, the substance that was dissolved, per liter of solution. So essentially you can write yourself a little equation for molarity is going to be equal to the moles of solute over the volume. Oops. Sometimes I get funny stuff going there, which has to be in liters. Okay. Now, remember that a solution is a mixture, and it's a homogeneous mixture, and mixtures do not have a set formula. From one solution of salt water to another solution of salt water, there could be a different ratio of moles to volume. And that's why we need this number to describe our solution. If I just say I have a saltwater solution, we know that salt is the solute and that water is the solvent, and that it's salt mixed with water. But we don't know exactly how much salt is mixed with the water because there's no set formula for salt water. The amount of salt can vary from one solution to another. So that's the purpose of having molarity, is to just quantify and describe that ratio of solute to the volume of the entire solution. A typical problem might look like this. And you can see here that we have the molarity of the solution. We know the identity of the solute, okay? We also have the volume of the whole solution. And using those, we can actually calculate first how many moles of KNO3 are in the solution and then convert that into grams. Now, we just had on the previous slide molarity. Oh, hold on. Funny stuff going here sometimes. Can I get that? There we go. That molarity is equal to the moles of solute, which in this case is KNO3, over the volume of the solution, which needs to be in liters. If we know both the molarity and the volume, we can rearrange this to solve for the moles of KNO3. We'd multiply both sides by volume, and we'd end up with molarity times the volume. Over here, it's going to cancel, so we would get the moles of the KNO3. So we got the molarity, 0.25, and the volume we need to put into liters, okay? You may move the decimal or do a little factor label to convert that, whichever you are most comfortable with. And you should come up with this number of liters. And when you multiply those, you get this many moles of KNO3. Now, I'm okay if you round that off to 0.038. Or if you decide to, keep it until the final. But we do need to make a note. There is 2 sig figs in the final answer because of this 2 sig figs right here in the molarity. Okay. There we go. So now that we know how many moles of KNO3, we know how to convert moles to grams because we're looking for mass. We're looking for grams. So we know how to convert the moles to grams, okay? We just need to add up the molar mass, 1 mole of KNO3. If we add up the molar mass is 101.11 grams. And so when we multiply and we round to 2 sig figs, we would need 8.3 grams of KNO3 to make this solution. Now, this is a very common task that you might have to do in a lab, maybe in a science fair project, maybe in college, prepare some of your own solutions for a lab. And if you know how much of the solution you need and what molarity, this is how you would go about weighing, calculating how much solute you need to weigh out. And then you would weigh this amount of KNO3 on the balance and then dissolve it in 150 milliliters of water. And that would be your solution, your 0.25 molar solution that you need. So here's just another one that has the variable in a different spot. In this one, you're trying to calculate the molarity. So you're going to need to get the moles of the solute. So take that right there and convert that to moles. I'll give you a minute. Get the molar mass and do that conversion. Now the molarity is going to be equal to the moles of copper chloride that you calculated divided by the volume in liters. So to calculate that molarity, we'll have to take those moles. Now I found the molar mass to be 134.45 grams. So I took the 15 divided by that and I got 0.112. I am going to round it off to 3 sig figs. I got to get a little better with this pen. Sorry about that, everybody. And this should be a 2. And this is moles of copper chloride. And you want to divide that by the volume, which you need to put into liters. Again, you could either move the decimal or you could certainly do the factor label. And I got 0.345 for the molarity of copper chloride. Now, it's important that you note what you have found the concentration of. That's the concentration of the whole compound in the solution. And why that's important is that you are often going to need to know just the concentration in molarity of the individual one or all of the individual ions. In this case, it's asking you to find the chloride ions. Now, this kind of goes back to what we were working on earlier this week, where you take it and because it is soluble and dissolved in water, we know that this is going to break apart to give you, dang it, again, it's going to break apart to give you 1 copper 2 ion and 2 chloride ions. Now, this is really important because we now know the ratio, that it's 1 to 1 to 2. For every, and that wasn't very dark, for every 1 mole of copper chloride that breaks apart, we're going to get 2 moles of chloride ions. So if our solution contains 0.345 moles of copper chloride for every 1 liter, because that's what the molarity means. That's how many moles are contained in 1 liter of solution. We know then that there will be 2 moles of chloride for every 1 mole of copper chloride, and we can just double this and get the concentration in chloride only. There are situations where it's just one ion that they really want to know what is the concentration of this one ion, because that's the ion that maybe is, toxic, and they need to know what's the concentration of this ion in this groundwater. And so it is important to be able to take the whole compound, break it down into the ions, and any concentration that you have like this of the whole compound, that should say CuCl2, sorry, it's because I'm struggling a little bit here to write without it. Just doesn't want to. There we go. But you need to take the concentration of the whole compound, the CuCl2, and be able to break it into ions and know that mole ratio so that you can see what's the exact number of those ions, how many particles of those ions. Remember, moles stand for particles. We want to know how many particles of just that ion are in every liter of the solution. So you'll see some practice problems like that, and definitely look back at this. Here's one to try. Try the top problem right here. Take the potassium sulfate, break it apart, and then just get the concentration of the potassium ions in this solution. I think this is one that we actually practiced earlier this week on the day that we learned the solubility rules. When this breaks apart, we get 2 potassium ions for every 1 sulfate ion. So we know if it's this concentration of the whole compound, 0.050, that means that it's that many moles. I'm trying to ignore that little line. I'm tired of doing that, but I don't know. I got to get better at this. But if we have 0.05, I guess I'll take it out, because it looks like I crossed it out, but I didn't mean to. I just struggle a little bit still with writing on this. So the 0.50 moles, that's the whole compound. But if we want to know just the concentration of the ion, we need to see that it's 2 to 1. We're going to have 2 potassium ions for every 1 molecule or mole of K2SO4. And so it's going to be 1.0 is going to be the concentration. 1.0 is going to be the concentration of just the potassium ions in this solution. Okay. So what if we needed to make that solution? It says here, how many grams of K2SO4? See, I can't make a solution with just positive ions. Like if you have positive ions in a solution, you've got negative ions in the solution too, because when you make that solution, you use a compound, and the compound is going to have both positive and negative ions. So if I want to make a solution with this K+1 concentration, I have to weigh out an entire compound to get that, okay? So down here, when I'm trying to say how many grams of K2SO4 must be dissolved, to prepare this solution, look, I can't use this number because this is just the potassium. I got to go back and use my original number. And that's one of the things that's going to be really important when you're doing WebAssign and some of the homework problems. If I'm looking for just how many grams of potassium are in this solution, use this, because that's going to give you particles of potassium, which you can convert to grams of potassium. But in this particular question, it's asking us how many grams of the whole compound. So I need to use the molarity of the whole compound. Remember earlier we used our algebra to get the moles of K2SO4. We would use the molarity times the volume. So 0.50 times the 0.3000 liters. And I'm going to get here that I need 0.15 moles. And I'm going to encourage you, start labeling what this is. This is the concentration of K2SO4. So this is moles of K2SO4. From there, it's a pretty simple, just, convert the moles to grams, which I already added up the molar mass of this. And it happens to be 174.27 grams. That's a 7. So make that a little neater. So it's a 27 grams for every mole of potassium sulfate. And when you multiply those, you will get 26 grams of potassium sulfate. So if I needed a solution with this concentration, the 1.0 molar K plus 1, I would have to weigh out 26 grams of K2SO4 and dissolve it in 300 milliliters of water to get that solution. Now, a lot of the problems that you're going to try on the worksheet, they're just variations of what we just solved using, different compounds and different ions. Certainly need your periodic table handy, your ion chart, but you know the definition of molarity. You can do the algebra and manipulate the equation. Sometimes you're going to have to calculate molarity, sometimes volume, sometimes moles of solute. Sometimes the moles of solute need to be converted into grams or milligrams, or reverse, you might have to convert the grams or milligrams into moles. But then this is the new part right here. Being able to split the compound into the ions and then use the mole ratio to get the molarity of just the ion that's in the solution. Practice that on the worksheet. Good luck. And, if you need any help, come back and review this, or certainly email me and contact me and ask for some help. Good luck.